The velocity, the unit of the velocity we know is one of them is in miles per hour. From the table, we have the data like at the point of the time t0, the velocity is 50. At the point of time 0.25 hours, the velocity is 50, and so forth. So from this table, we're gonna part A, we're gonna sketch a curve passing through the data point. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 points. Okay, we're gonna put them all into one graphing area. And then part B, we're gonna find the left Riemann sum approximation to the displacement on the interval 0, 2. You see the first time is 0, the last point of time is 2. So from 0 to 2, we're gonna make it into just 4 sub-intervals, and then find the approximation of the displacement using the left Riemann sum. And then part B, we use the midpoint Riemann sum and use it to approximate the displacement from 0 to 2 with n equals 4. So part B and C, the whole idea is to find the approximation of the displacement from 0 to 2 with the same number of the subintervals. And from the data that provided, we have 9 data points. If first of all, let's sketch a graph, and we can use the graph in part A to determine or to set up the approximation in part B and C using either the left or the midpoint approximation. This problem, it doesn't provide you the function notation like the last two examples, like f of x equals e to the 2x, or f of x is cosine of x over 2, but just give you the coordinates or the order pairs. So to sketch the graph, see the t as an independent variable. If you recall the velocity, which is the function of the time, right? V depends on the time. So if you compare x and y, so x as the independent variable, y is the dependent variable. So we can see this as y depends on x, or the v depends on t, or the velocity depends on the time. So to sketch the graph, the point of the time from 0 to 2, I'll do my best to draw it by hand here, and see all the function values or the value of the v, they all are positive. And the numbers, they vary from 50 to 70. Do not worry about making the right scale, since the lowest number is 50. So we can like adjust the scale, shrink the scale, and then starting at 50, and then go by the increment of the 5, just for our convenience. So 50, 60, 70, that's the highest number. So the vertical axis is the axis for the v, or the velocity. And the horizontal axis is the time t. And we make it into the interval like from 0, 0 0.25, 0 0.5. I'm going to write it down here. 0 0.75, 1, 1.25, 1.5, and the next 1.75. The last one is at 2. It doesn't look like equal subinterval, but it's all good. All right, at 0, the function value is 50. The point is to suggest the graph. Okay, we're gonna use the graph here to help us set up the next two examples. I mean part B and part C. So at 0, the velocity is 50. At 0.25, velocity is also 50. 0.5, velocity is 60. 0.75, another 60. At 155, 1.25, 65. And 1.5 is 50. Let's go down here. 1.25, 60. At 270. And then if we sketch a smooth curve, that means we're gonna draw the line to connect all the points together. Doesn't have to be perfect. Okay, that is part A. So from part A, we're gonna use it to find the approximation using the left and the midpoint. The other pair that we have, we're gonna do it from the interval at 0 to, from the point 0 to the point 2 with n equals 4. If n equals 4, we're gonna make it into 4 equal subintervals. So that means the delta, this time is not x, right? It's gonna be the delta t, or the difference of the t from one point to another point is gonna be from the total length, which is the difference of the a and b. Your a is 0, your b is 2. So b minus a divided by n, or 2 minus 0 divided by 4, or 1/2, or 0.5. So that means you're going to make it into 4 equal subinterval with the width 0.5. From the graph, you just make a partition at 0.5, and the next going to be at 1, the next going to be 1.5, and the next going to be at 2. Now we have 1, 2, 3, 4, 4 equal subintervals. Question at this point. Okay, and your goal is to approximate the displacement. How do we make a connection of the velocity and the displacement? We call the formula v equals the distance divided by time, right? Distance divided by time. The displacement is the net change of the location, the last point and the beginning point, the displacement. So if you adjust the velocity formula here, so that means the distance or the displacement is the v multiplied by time, okay, or the v times t. And what is the v? The v is the dependent variable. The t is the independent variable. And basically the displacement or the distance is the area under the curve, because the v times t, v is the height of the bar, and the delta t is the width. Okay, the delta t is the width. So if you find the area, that means the length times the width, and the quantity, that is the displacement within each subinterval. Okay, so to find or to approximate the displacement, that means we're gonna find the area under the graph from what we get from the information provided from 9 order pairs. So the first one, or not the first one, in part B, you are going to use the left Riemann sum. Okay, left Riemann sum with the n equals 4. For the left Riemann sum, I'm gonna go back to the graph real quick. For the left, since we have 4 subintervals, so the left Riemann sum, use the left end point, left end, left end, left end, left end. So you're gonna use t at 0, 0.5, 1, and 1.5. Does it make sense? So I'm gonna make a list here. So the t that we're gonna use for calculation gonna be t at 0, t at 0.5, t at 1, and t at 1.5. 4 points as the left 4 points. And then for part C, just get ready for part C. Part C, we're gonna use the midpoint from each subinterval. Okay, the midpoint, what we're gonna use, I'm gonna use different color. For the midpoint, see the midpoint gonna be 0.25, 0.75, 1.25, and 1.75. I'm gonna bring it to the problem to get ready. So that means the t that we're gonna use to compute for each midpoint, the first one gonna be t at 0.25, the next is 0.75, the next is 1.25, and the last is 1.75. So we get points of calculation. Okay. So with the point of calculation, now we're gonna come back to set up to do the process. Then the approximation of the displacement. So the displacement is approximately equal to, now it's going to be the sum of the velocity at the points that we listed and multiplied by the width or the delta t, or the change in time from n equals 4, the delta t is 0.5. So we're gonna pick the value from the table, the v or the function at 0, plus the v at 0.5, plus the v at 1, plus the v at 1.5 for the left Riemann sum, and then multiply by the delta t. And then from the table, at 0, we take the value 50, and the next 60, 55, 50. So the sum of 50, 60, 55, 50, and then multiply by the delta t, which is 0.5. And then put in the calculator. The number should come out to be 1 point, no, 107.5. The unit is miles. You can verify the number for me. Well, this time it's no function involving just the values from the table that we're going to use. Okay. Are we good for this part? Okay. And then same way for the last one, we use the midpoint Riemann sum. So this case, since we list the points of calculation, t is 0.5, we're going to use the function value at those points. So the displacement approximately equal to the sum of the velocity at 0.25 plus the velocity at 0.75 plus the velocity at 1.25 plus the velocity at 1.75, and then multiply by the delta t. And then from the table, we're gonna add the value 50, 60, 65, 60, and then multiply by 0.5 and get the number. Let me see. It should come out to be 117.5. Unit is in miles. So two different ways to approximate from the data that we have. So we do not have to rely on the function notation all the time, as long as we have enough information, and with the information about using either the left, the right, or the midpoint Riemann sum approximation, we can use whatever we have to find the solution.